Okay, I guess we'll start then. So thank you for joining us. First, I'm going to tell you something about the company that I work for. Then I want to give some theory about the cobots and how they are used in practice. Then I want to do some exercises so you will actually program the cobot, so you can learn how that works, of course. Okay, so the company that I work for, MAIT, which stands for My Automation Information Technology. Work as it does. Okay, so some numbers. We do industrial automation. So yeah, we do project-based jobs. So we have about 600 plus completed projects. We have about 104 engineers, and a lot of them are software engineers like myself. I'm a junior software engineer, and we have 5 locations throughout the Netherlands. They are located in Almere, Assen, where we're at right now. So we have a couple of offices right above you. Our headquarters are in Deventer. We have a location in Gorinchem and a location in Eindhoven. So it all started in Deventer, which is our headquarters. Then we moved to the south of the Netherlands. So a little, first we were located in Son, and now we have an office in Eindhoven. So we are a little bit bigger in that region of the Netherlands. And then we moved to the western of the Netherlands, so Almere and Gorinchem. And now we are also trying to reach the north of the Netherlands, which is done through our location in Assen. So these are some of our the things that we do at work. So we mostly do industrial software development, electrical engineering, and IT software development. So those are kind of the branches that we offer. A lot of our engineers are software engineers, like I mentioned. The electrical engineering is more hardware engineering. And then we have what we call hybrid engineers, which is the IT software development. And they basically make the connection with the factory and the offices. So you can get data from the factory into the offices and optimize it and stuff. Next to those, we also do consultancy, training and coaching, and a little bit of product development. So we have our own website, the IA Professionals Academy, in which we can educate engineers. And we basically try to fill the gap between school and the actual work field. So this is a small section of our customers. Like Friesland Campina is a really big name in Holland. They do dairy stuff. And Ekels is also a really big name, a little bit more in the north here. They do a lot of electrical engineering, also a lot of projects, and we help them with those. We do a lot of work for IKEA. So they have these big automated, storage rooms. So right now, if you go to the IKEA, you have to walk with your pencil and you write down what you want and you take it from the storage. But they are actually working on big plans where they implement robots to get your stuff for you. So that's all automated, and MIT is also a big part in that. So then I wanted to give some theory about how robots are used in practice. So I have a small video for that. Try and not make it as loud. So this a typical place where you see robots. So you saw about 10 to 15 robots standing there. They're just moving some plates between the machines. And then you see some some humans doing the final inspections on the products. So yeah, that's basically what robot arms are used for. You can put like 10 to 15 people there, of course, moving the plates between the machines, but it would be quite dull work. It's continuous, and you can use humans for more intelligent work. So instead of putting humans there, just put some robots there, and they can do the dull work for you. But also, of course, to reduce the hazardous situations. So those machines can put quite a lot of weight, or maybe they have uh, maybe they have sharp knives on them or something. And if a human doesn't pay attention, tries to put a plate there, and the machine pulls down on it, then you might get hazardous situations where you cut off an arm or something. So first of all, robots won't get distracted. And second of all, if a robot gets an error or whatever, and you break its arm, whatever, costs a lot of money, but it's better than cutting someone's arm off, of course. And then also reducing the labor-intensive work. So those plates can weigh, let's say, up to 20, 30 kilos. If you do that for 8 hours, yeah, you're not gonna make it until you're 65. But also, one of the most important things nowadays is to have more accuracy and repeatability. So that's also where robots are great for. So I have another video where a robot assembles a PCB, so a printed circuit board. And here you can see that it's, of course, it's way faster than a human would ever be able to do it, but it's also way more precise, and the repeatability is far better. So it's taking out all of those little components and putting them exactly in place. So it's quite a long video, but I'll just skip to the end. So you can see all the components are placed nicely. So this is done in about 2 minutes. And if you were to let a human do that kind of work, of course, it would take far longer, and the repeatability and accuracy would be lower. So then I wanted to show you some robot projects of MIT. I think this has Dutch commentary on it. Yeah, it does. But this is a robot which assembles, yeah, what do you call it? Not sure what the English word is actually, but it's for trucks at the back of the wheels, so it doesn't wheel archers. Thank you. Yes. So one of our engineers actually programmed this in combination with a Siemens PLC. Een andere robot plaatst loopings en argumenteert de kat in combinatie met de sprayer. So there's two robots working together. They have to communicate with each other, of course. So yeah, then I have one more project of which MIT was involved in as well. This is actually a quite fun project. So this is a robot which stands in a resort in Curacao. And customers of the resort can order their drink, and the robot will then make the drink for them. So it's quite overkill, of course. So you can see it takes a cup and it makes the drink for them. Now, of course, this is not very advanced because it basically just the work a human can easily do as well, and it's quite a bit more expensive. So also now a customer orders a beer, and it just opens the fridge, takes out a beer. Morning. And it can even open the beer and give it to the customer. So these videos that I showed you were actual robots. Now, of course, what we have right here is a cobot, which is quite different. So there is one big difference. So between this video and the other videos that I showed you. So this is the exact same cobot as we have here. And if I play it, you might notice one big difference. So this is, again, not the best example video because the guy can just place the boxes himself, of course. But there is one major difference between the videos I showed you, or the last two videos and this video. And that is that for a cobot, you don't need the entire cage around it. So say this is a continuous process, and the cobot places the boxes on the pallets. You can just go there with your forklift, pick them up, and place a new pallet. So that's quite handy. And of course, humans can work alongside them. So that's the main difference between robots and cobots. Cobot stands for collaborative robot. So humans can work alongside them. Why can they work alongside them? It's because they have torque measurements on each joints. So this cobot right here has 6 joints with motors, which can move each of them. And the motors have they measure the torque continuously. Next to that, they have a lot of safety implementations in the software as well. So we'll get to that later. So the pros of the cobots is that they can work alongside humans. They are really easy to install. You don't need to install the big cage and stuff. And they are easy to relocate. So as you see here on our cobot, we've just put it on the table with some wheels underneath. So if we want to use it here, we can use it here. If we want to use it in another room, we can just move it there. And we can use it there instead of having to move the entire cage and, well, everything. Next to that, it's also more cost effective. Not only because they are cheaper, because they generally are cheaper, because they are smaller generally than other robots, but also because you don't have to train engineers. You don't have to buy the entire cage and the sensors and safety implementations that come with those. Now, the cons of the cobots are that they have a reduced payload, they have reduced speeds, and they are usually quite a bit smaller. So yeah, this is the cobot that we have here at the Tech Hub in Assen. It's the robot is from Hanwha. It's HCR-12. So if you can see back there, HCR is just their brand name. And they also have a 3 kilograms, 5 kilograms, and 12 kilograms. So this one is the largest, which can handle the biggest payload. And the main components are the controller, which is down here, which is basically just a computer. The teaching pendant, as they call it, on which the software, which it's basically just the screen of the computer, and of course the robot itself. And we'll get to the GUI later. So yeah, this is the anatomy. So you have a couple of joints. You can see here where it can move. So this is the first one, the second joint, the third, the fourth, the fifth, and the sixth is alongside the tool. So yeah, they have these fancy names for the joints, but yeah, we'll just call them joints 1 to 6. Then there are 3 reference frames. You can add reference frames for yourself if you wish to. But the main 3 reference frames are the flange, which is basically here without the gripper. You have the tool center point, which is a reference frame which you'll have to align yourself. And it's basically at the end of your tool, so where it actually grips the product. And you have the base. Now for the grippers. As you can see here, we have a Shunk gripper. So Shunk is a different company than Hanwha, which I found quite weird actually, because if you buy a robot like this, it will actually come without a gripper. So there are special companies like Shunk which provide certain grippers. Now, why is that? It's because there are a lot of different types of grippers for different applications. So as you can see here in the top left, you have a pneumatic gripper. So if you want to grab flat surfaces, you can put those on it and draw vacuum, and then you can tilt things. This, for example, is a gripper which also has two handles, but it can measure the exact dimension of something it grips. This is another gripper from Shunk, which has 3 grippers and also has some magnets in it, so it can grab certain metals and reduce the payload for the for certain things. And of course, you have also way more advanced grippers, which represents a hand. They can also be pneumatic or whatever. So here I have another fun project of ours, in which we can see a double gripper. So this is the same cobot as we have here. And it uses one of its grippers to take out the finished product, moves around and puts in the other product. So here you can see the same elements, of course, as I mentioned before. It's basically dull work to put a human there and make it replace one of the products every 10 minutes. And it can also cause hazardous situations. Okay, so first I wanted to talk about the software. So the software is called Rodi. This is the software that you program the Hanwha cobots in. So one of the main things, of course, for cobots is the safety aspect. So these are all implemented into the software, and there are certain variations that you can take with them, but they are limited to some extent, of course, for safety. So here we can see you can change the amount of torque that the joints, or the maximum amount of torque that the joints can measure. You can change the maximum amount of force, and you can change the speed. There's collision mitigation, so it can actually detect when when it has a collision with something, which you can turn on and off. And you can also, for each individual joint, you can limit the speed. Furthermore, you can also implement safety boundaries. So let's say, for example, if we have this robot set up here and we have the digboard there, we can implement a safety boundary in front of here, so we can make sure that the robot can never move there. So the software sees where it is, the safety boundary, and if it approaches that location, it will just shut down and tell the user that it can move there. Now, to make the robot move, that is done using move commands, and the move. Oh, I think I should shut that door. Deze even dichter. Sorry. So the move commands are made using waypoints. So which is basically a coordinate system. So you can tell the robot to have its first move command right here. So it will start up, going to that position, then make a second move to this position and third move to this position, which are just coordinates in the space. So there are 4 kind of movements: a joint movement, linear, arc, and circle movement. So a joint movement is used to get to a certain position the quickest way possible. So it will move each of its joints in a certain way to minimize the joint movement as well, and to get to a point as fast as possible. The linear movement is actually focuses on keeping the tool center point, so the tool itself, as straight as possible. So that is mostly used for moving liquids or whatever, so you don't have to spill anything. Yeah, and it uses the same way. So the joint movement actually uses rotational coordinates, and the linear movements use linear coordinates. So X, Y, and Z instead of rotational. Then there is an arc movement, which is well, not commonly used, but for an arc movement you implement 3 waypoints, and the robot calculates the arc using the waypoints. And for the circular movements, it's the same. You implement 3 waypoints, and the robot calculates the circular movements using those 3 points. So here are some of the command blocks. The move command, in which you can set which type of move you want. There's a wait command, and we'll get to that later as well. But you can make the robot wait. You can, for example, make it wait for a certain amount of time. You can make it wait for a digital input. You can make it wait for an analog value. So it can also communicate with devices in the field. And there is a set command. And with the set command, you can set values to certain variables. So for the gripper, there are 4 digital values. 1 to open and close the gripper, and there's also feedback, so you can tell when it's closed or when it is open, which you can also use, of course, in the wait movements. And one of the easiest way to program the robot is using the direct teaching method, but we'll get to that in a bit. Yeah, first I want to show you the software. This is what it looks like, the programming aspect of it. So here you have your main program. So it's basically done by placing certain blocks after each other, and it will just linearly go through those. I think you can barely read this, but so for each command block that you implement, there are certain settings which you can change in this box right here. So here are the different command blocks that you can implement. So yeah, these are the most commonly used, and there are some extra which we'll get to later as well. And you can add variables. So yeah, that's done here. So then I wanted to move to the first exercise actually. Or well, what I first want to do is something a little different. I will open up this. So usually the software is on the teaching pendant, but of course it's not really handy to have that for the presentation. So I will take out this cable. and put this one in. And now we should. Yeah, so now we have the software on here. So let me show you. Let me plug in these. So now these should be connected. So yeah, here we can see the software. So these are all the menus. We won't go into detail of them. But one of the fun things is the safety settings and the motion limit, which I just showed you. So I can actually let you feel. So now we have the torque set to the minimum, which is 25 Newton meters. So if I make, for example, so this is, by the way, how you program the movements. So you implement a move, you press on set, and then you get this GUI in which you can program the coordinates for the movements. So let's say for our first move, we want to 0 the robot. You can press jog and make it move there. So now it's at its 0 position. And we can implement another move. Oh, set. And let's say, for example, we want this to go to -90, which is towards me. Nice. So now if we apply this in the software and we say play from starting point, we have to move it to its original position, of course. And then we can set it on replay as well. And then it will just keep on repeating this function. So what you can feel now, if you want to come up here. So right now I have the torque set to its minimum. So if you put just a little force against the movement, you'll see that it stops. Is that somewhere? Yeah, yeah. So not really a lot of effort, right? So it says collision is detected. Do you want to continue? I can press yes, then it will start moving again. But if I now, for example, turn it, instead of 25, if I turn it to 75, our robot is in motion, yes, stop it. We can do the same. Yes, turn it on, play from starting point. So I think you can feel now that you'll have to put in a lot more effort. I will actually hold the table so you don't push it over. I don't think it's going to be that bad, but you can try stopping it right now. Yeah, see? So it takes quite a lot more effort. So even if you put it on 150, we actually tried that last week as well. You could actually like hang on it and it wouldn't even stop. So it should just continue now. Okay, but then for the first assignment or exercise, I collected this recycling bin. And I wanted to ask you to use the direct teaching movement to pick up a cup from the table and throw it in the recycling bin. So I will go here. So it's quite a lot easier to program. Okay, so you can use the set and direct teaching here below. Then you will see that this turns blue and you can actually, so the motor shut off and you can just place it anywhere. You can move any joint you want, like that. I will put this down. And I have collected some cups. So yeah, just try and make a program which we'll throw away. Yeah, do your thing.
Can I also open and close the gripper now?
I don't think you can now. Well, you can a little bit, but of course you'll have to implement that in the software to open and close it.
Okay.
Yeah, it's quite unstable with the wheels. So you can also move this joint.
Yeah.
If you want to help Ruben, then you can, of course.
This is a sort of manual operating mode.
Yeah.
How do you exactly trigger that?
So you.
Is that somewhere in the
Yeah, yeah.
menu right here?
So there is with each, so it's called direct teaching. So you can just implement a move, and I think you know that with a move you just tell it to move to a certain coordinate.
Yeah.
So if you set it, you can manually set each joint as well.
Yeah.
But you can also just click direct teaching.
Oh, with
and then
direct
and then you,
teaching, then you can like manually move it. Oh,
yeah,
okay.
yeah. So you can manually move it indeed.
Yeah. Okay. Yeah. Oh, then I know that.
So, but I think okay. So that's the first move.
Yeah.
So you can exit out of direct teaching. Just press direct teaching again, and then it saves those coordinates and press OK. So that's the first move. Now we want to open or close the gripper. We can do that with the digital in outputs, but I will show you something which is a bit easier. If we go to commands, Rodi X, there's actually a pre-designed variable. You can implement that, and you can just tell it to open or close. So say we want this one to close, you can execute it. So in the program, it will execute that automatically, of course. So yeah, so the first move moves towards the cup, and the second one closes the gripper.
Is the gripper force actually also monitored?
I think you can with an analog value. So it measures the amount of amps it sends towards the gripper.
Okay. So I guess now it's closed. We have to move it in.
Yeah. So now you can click on the next movement. You press the set button, just a little bit up to the right. Yeah. Then you can use direct teaching again.
Dat commando voor die gripper, hè?
Ja.
Daar is een eigen driver voor gemaakt of zo? Of,
ja.
Ja.
Ja, klopt. Yeah, the table is quite unstable, which can be a bit annoying.
I guess if you open the gripper now, it should.
Yeah, right. So you can save the movement. So it has the coordinates saved again. Sorry? Yeah. That's okay. So that's the coordinate saved. Yeah. So there's two ways you can implement it again, but you can also press edit. Right, and then deselect the one you have selected now. Yeah, but just press on it. And then you can press on the gripper command, copy it, Yes, and then press on this one. So it also always places after the one you're clicked on. So if you paste now, yeah. And then you have to exit out of the edit mode. And you do actually have to change the name, or otherwise they link to the same object. Okay. So if you now change this one, it will also change this one. Okay, so above there, yeah, just make it anything you want. It doesn't matter. Yeah, sure. Yeah. So now there are two different objects. Right. Then we have to open it. Yes, correct. Press execute. You can to test if it falls incorrectly. Okay. Should work. So to test it now, just press apply. And we will put a cup right here. Press OK. And then on the big play button. Play from starting point. So then, yeah, you have to press on the move and keep pressed on it. Then we'll move to its starting position. That's quite unfortunate. So we can also learn from that, of course. So what you might want to do is for the first movement. So this one is like actually being inside of the cup, and then you can add a movement which just on top of the cup, indeed. So you can use direct teaching again. Yes. And move it slightly up. I think it was right there, right? And it doesn't have to be exact because you are exactly grabbing it with your second movement. So. Okay, then you have to press apply again. It just checks for errors, basically compiling your code. And then press the play button. I think it starts immediately. Okay. Let me be quick. Okay. Nice job. Works quite well. Nice. So now you can, of course, say the cup is filled with liquid. You might want to implement a linear movement, so the tool stays centered. But that's for later classes. Nice. Yeah, that's the pause button. You can also press the square to stop it. Stop the entire program execution. Yeah, nice. Okay, great. Thank you. Then I will go on with the rest of the presentation. So those were basically the most basic functions that we used. I don't know if you are familiar with programming of any sort, a little bit, yes. So of course, in this program, you can also add certain variables. You can add if statements, loops. You can use case statements, which in this software are called switches for some kind of reason. And you can implement subprograms, which are basically your functions. Threading, so you can have your main program running, and you can thread some sort of process, so it will run next to the main program. And we have the set function again, of course. So now I have a bit more advanced exercise, which is to write a program which picks up one of the cups again and throws it into one of the 4 holes. But then I want you to write a program which picks it up, throws it in this hole, for example, picks up another cup, but then throws it in this hole, picks up another cup, throws it in this hole. So yeah, basically move along all 4 holes using the different functions that are available within the software. So yeah, we'll switch back to here again. And then let's say go right ahead.
We should use like a sub program.
You can write a sub-program.
But otherwise, you could just implement it like different commands, right?
Yes, you can, of course, program different move commands after each other, but you could also use like an if statement. So add a variable which says amount of cups or something, and then if amount of cups equals 0, because this movement is the same, pick it up, move it to here, and then throw it in this one if it equals 0, and if it equals 1, throw it in this one. So something like that. But I'll let you think about it.
Okay. So I guess picking up the cup will always be like the same.
Right. So I would indeed put that in a subprogram. So to do that, you have to go to here, to sub. And here you can write your subprograms. So add a subprogram. Yes. And then if you press on that, I think, yeah, then you should be able to implement movements in that subprogram.
Okay. This is my subprogram now.
Yeah, that's your subprogram,
Okay.
which
So
you can later drag into the main program. Should I hold the table? It's quite annoying.
okay, I guess we have to open the paper first, or can we just?
I think in direct teaching we can just a little bit of force or not.
No.
Okay, then it's still activated, so it's still sending the force to it.
Just exit out of it, or?
Yeah, you stop the direct teaching. Oh, you have to press OK, I think. Or do you want to open the gripper first? Yeah, then you can add, or what you can also do. Let me show you. I didn't mention it, so I think you can. Where is it at? That's IO status. Yes, save it. So here you can. So this is just a general IO of the computer, but here in the tool IO status, you have the feedback and output signals. So as you can see, indeed, the digital output, which is the close command, is high. So that's why we can't open it like this. So if I press this, it's low, and now I should be able to open it. So yeah, you can also just use these to open and close. And you can also see here the feedback. So yeah, but we wanted it open, right? Yes. So yeah, so it's open now. And then we can go back to the programming, subprogram. Yeah, right there. Yeah, it has the position saved now. And you can also move this joint. You'll have to put a bit more force if you want to do it, of course.
Somewhere over here would be sufficient.
Yeah, definitely. So of course that's how you program them in practice as well. So you make like an approach move where you get near to the subject, and then you make the movement that you actually grab the cup or whatever. You make that very precise. But it's generally you just make a rough approach move, then grab it.
So in this case, would it make sense to actually put like a variable here to always make sure that the gripper is open before I go down? Or?
Yeah, definitely.
What was that?
So that's in commands, which is next to edit. Yes, and then at the top, row the X. Yeah, that one. So yeah, I think if you execute it, it powers the. Yeah, it does. Doesn't matter, but I think it turns the output high. So.
Okay, so we add like a new command, I guess.
Yeah. So you can also, by the way, if you exit out of direct teaching, I'm not sure if it works because it does work on the teaching pendant, but you can also move the joints using this. So because you are already very quite decently above it, you can also use these to just make it move up or down. So this actually targets the tool positioning or the tool center point quite well. So if you just make it go down, it actually goes down quite straight. So you can just make it do like that, which is a little bit easier for the small movements than the direct teaching.
Okay, so I guess.
Yeah.
Copy paste variable again.
Yeah, or just add a new one, whatever you want.
Any subprograms can you actually have?
I'm not sure exactly how many, but I think it's quite a lot.
Okay.
So the computer, of course, has a certain amount of memory. So if you exceed the amount of memory, then you can make any more of them. But I think because it's actually a quite an advanced computer, which is in here, I think you can have a lot.
So would it also not make sense that like different movement just lifting it up a bit and then afterwards like
Yeah.
have a linear movement or?
I think so. Yeah. So say for example, move it up.
I'm leaving actually. So
Okay, is goed. Hey, thanks. So exactly, say that you were moving something with a liquid inside of it or something. You would want the tool center point to stay very still. And if you make a movement from here to down here, of course, the robot wouldn't know there's a table, so it would just drag it right through the table. So it is indeed quite smart to do it like this.
Okay. So now we can like here, like this here.
Yeah.
Can I still use like directly change them or?
Yeah, definitely. Yeah.
So we said that we wanted to just approach the cam, right? And then afterwards we
Right.
decide what we want.
Yeah, that's what I would do because you're making a subprogram right now. So I would program the subprogram indeed to grab the cup, move it just anywhere here, and then make an if statement to do it either there or there or there. So I will hold the table. I think if you go quite subtle, it shouldn't move the table, but you never know. Yeah, anywhere is fine, definitely.
Okay, so I guess this is our subprogram now.
Yes. So you can test that, of course, or you can just move along with the program, but whatever you want.
Okay, right. That's it, but then we actually have to implement like a gripper opening.
Well, yeah, not really. We can just move it.
Okay.
just see if it works.
Yeah,
Bec-
yeah. Press apply.
Yeah, apply. It's basically compiling your code. See if there are no errors. Yes. Oh, we have, by the way, we have to go back to the main program.
Okay.
Because you are in subprograms now. Yes. Yeah, you can just delete the, so go to edit. And then select all of them except for the first one. That's an initialization block. So I mean, you can delete it, but yes, and then delete those.
Yeah.
So then go out of edit mode, and then you can choose the subprogram. Click the initialization. You can, if you click this one again, yes, then you can select subprogram. Then if you press it again, I think it should. Why is it not? It's weird. let me check. Because maybe we have to press save here first. Oh, it's quite weird. You have to press this first, I guess. So that's your subprogram. So now it says it will just execute this. Oh yeah, it also shows it right here. So yeah, let's apply. And let's see what it does. So move to the starting point. And I think it will drop the cup first, but yeah. So as you can see, it holds the tool center point really steady with the linear movement. So you can also see if you look at the different joints, it makes quite a complex move just to keep the tool center point as steady as possible.
Right.
It's quite cool. Okay, but that works, so nice. Good job. So now after this, we can make it move to its last position. So if you just press this and hold the move button, it will go to that position. Mm-hmm. So you know that after the subprogram, this is where it's at. And maybe we should, oh God. We should do this again. Here it is. So like this. And then close it. Or did we pick it up here? Yeah, I think we did, right? So like this. So. So yeah, you can actually also see here about what you asked. So it sends 0.1 amps right now. Okay. So I think if we turn this off, you can see that it's not exerting any force anymore. Mm-hmm. And if we turn it high, it is. So yeah, you can read out that analog value. So yeah, that's where you're at with your subprogram. Okay. So now we just need to make a...
So what was the exercise? We first want to pick up the first one and put it in like...
Yeah, put it in one of the holes. So let's say this one. Then after it's done that, it needs to pick up another cup, throw it in this hole. Yeah, then repeat that for every hole.
We need some kind of variable to count like where we're at,
right? Right. Okay. So we can go to variables next to commands. Yeah, so you can just add a variable. So there's different types. String, Boolean, and number you're probably familiar with. Yeah. And position and joint is a linear position, so 6-dimensional linear position. And the joint is our rotational coordinates. And an array is an array. But for now, we just need a number. You can press on it again, on the name. You can change the name to, I don't know, amount of cups or something. You should be able to type as well with the keyboard.
Initial value 0.
Yes, definitely. Yeah.
Okay. And okay, so then we put in like an if statement.
So you can press the subprogram again. Yes, so then it exits out of the subprogram. And if we add an if statement now, then that's just an if statement. And at the with the top bar, yes, that one, you can implement whatever you want. You need to press this one first. It's quite annoying. Yeah, cup. So if cup equals 0.
Okay.
So yeah, now here you have the line for if cup equals 0.
Okay.
So now you can just put anything in there. Movement indeed.
Okay. So then we position it. Okay.
Should I hold the, the thingy again? I think so. Yeah. Should be.
Okay. And then we open the gripper.
Yeah, that was at commands.
Oh,
Yeah.
fine. Okay. Okay. Then we call our subprogram again, I guess.
No, because well, yes, you can, but we have this program on repeat. So basically, it initializes, performs the subprogram, performs the if statement, and then again subprogram. So it keeps on repeating that.
Okay, but then we have to make sure that the variable changes.
Right. So we have to increment the variable.
Okay. And how do we do that?
That should be able to do with the set. So then we go to var variable. Then for variable, I think we can just go to the input expression. Yes. And then again, you have to press. It's quite stupid, but.
Okay, then we set it to 1.
Well, yes, but we want to increment it with 1. Because now you check if it is 1.
Yeah,
but,
true.
yeah, that's also quite weird. You can't assign. So you can't say it equals 1. You have to actually increment it. Right.
But will that now increment it?
Yeah, it will. So now you say cup plus 1.
Cup equals cup plus 1.
Yeah, yeah, correct.
You have to.
I have no clue why that is there, to be honest. You can say expression, or I think yeah.
But now it says like cup equals then the expression, right?
Yeah, but yeah, it does. But yeah. Anyway, it works either way. So
Okay.
if you can change the expression to I think make it a string, but this works.
Okay. And now
So,
we
yeah.
have to assign like a new if statement, I guess.
Yes.
For 1.
Correct. So we can go to the if statement again. And then on top of there, you can say plus else if. But then you can add another if statement. Let me hold the table. Yes, should work, should work.
Okay, then we increment it again, I guess.
Yes, but what we can also do is you're now copying these things to each if statement, but we can of course just put it after this if statement,
Right.
because
Okay.
otherwise you have to copy it 4 times.
Sure.
So
Edit,
yes, correct.
then delete maybe this one,
Yeah,
then copy these two,
yes, correct. Copy them.
or cut.
Yeah, cut. Yeah.
Okay.
So yeah, then you have to press the if statement. Oh, that's a subprogram. Yes. So I think if you paste it now, it should paste it after. It didn't. Okay, try again. I think that's. Yeah, now it should work. Yeah, yeah, great.
Okay, right. Okay. So now we just add like more cases, I guess.
Yeah, yeah, definitely.
Or we didn't even assign though.
No, not yet.
So how do we do that?
Yeah, press it again.
Okay, then up equals 1, I guess.
Yes.
Okay.
Yes. Same plan. Oh. Yeah, should work. Gravity is always the same. So.
Okay. Up equals 2 then.
Mm-hmm.
And now another one, yes.
Yes.
Okay, but the thing is now we are keeping commenting like the variable, right?
Right. So what you could do is in the third if statement. So if cup equals 3, so yeah, then you can say -4, exactly, for example.
Because afterwards.
Because afterwards it will increment, and then it's back to 0 again. Yeah, you can use the set function again. Okay. I think that should suffice.
So can you just apply it then? Or?
Yeah, yeah. Might want to take this out. Yeah, you can just start it now and see if it works.
Can just move it or?
Yeah, move. Yeah. I think we did not implement a open command in the beginning, or did we? I'm not sure. Just try it, I guess. Okay, we did, yeah. So, first one. Okay, second one. Nice.
Can I do a video?
Yeah, of course. You might want to wait for it to restart, but oh, it's the recycling robot. Seems to be working, so nice job. So yeah, now again, if I just will stop, no worries if any human gets hurt. So then we can start it again if we'd like to. Now the table did change a bit, of course, because of my brutal action. So it might have lost its orientation. Let's see. Yeah, nice. So yeah, that's one of the cons of this transportable table. Okay, nice. Cool. Good job. Right, then I will go to the final part. Yeah, this one is not. Sorry. No, we didn't. This one is not really working. It can't climb it. So I don't think it's anything special for the presentation anymore. Yeah, so I wanted to talk about some third-party offline programming tools. So of course, what we're doing now is quite fun. We can move the robot. You know, you have to be here and using direct teaching, move the robot. But it's quite it's not really convenient, and especially nowadays. There's a lot of working from home and that kind of stuff. So what you can do to program the robot offline is use some third-party tools. Which have a replica of the exact same robot, and you can use those tools to program movements and stuff, and import CAD objects. So I think as a mechanical engineer, you're quite familiar with those. Yeah, so you can make a replica of your working environment and use the third-party software to program it like that. So for this example, I've used RoboDK. I will have to switch around some USBs. One moment. Let me just take it from here. So I'm now running a free version of RoboDK. And so what you can do here is they have a library. Press this, opens my other computer. And they have a library with all sorts of computers. So it's a really long list. They basically have each and every single robot or cobot there is available. So for our robot who want to search HCR-12, you can just open it. And then it should add a second robot. So really easy. Now I have prepared the same robot as we have, with also the same gripper. So yeah, you have to, of course, import the gripper from the Shunk website, or maybe if you have made or if you have a specially made gripper, then you need to import those CAD files or even make it yourself. Yeah, I've prepared that for now. And the way this works is if we press Alt, we can, let me see if I can get it, you can just move the robot anywhere. So in each of its directions, the software will calculate how the joints have to move. So some nice things about this is that you can, for example, if you press View, you can show the workspace, so you can see exactly where the robot can reach and where not. So you can change it like this and make these movements. But yeah, you can see exactly what can the robot do and what can it not do. Let me turn this off for now. So how do you program with this? It's quite easy, actually. Let me move this again. So as you can see here, I have made one target, which is called home. So that's basically how you program movements with this. You can drag robots anywhere, add a target with this button up here, and it adds a target. So target 2, say, I don't know, move 1. So then you have that as a target. Let's say I want to stretch the robot up high, like this, add a target, and now call it stretch. So now you can see if we press the movements, the robot can just move between those. Now to make this into an actual program, you have to add a program, of course. And then we have 3 buttons here for a jog, a linear, and a circular movement. So for now, I will just click on the or on the target. So let's make the first movement a jog. This one is going to stretch. So the first is a jog to home. Then go to move 1, make that a jog. Then go to stretch, make that a jog. So it's basically the same as in the Rodi software. It will just keep on executing this program. So let's put this on a loop and run it. Oh, it's quite fast now. So this is the movement that it makes inside of the software. Now, usually, you would be able to connect this software with the robot. But for this robot, of course, there are drivers missing. So we cannot do that, but I can show you. You can generate a program. So it generates a program like this, which is basically a function of the program that you've just written. And you can copy the main components. And then Let me see, where did I have my hard drive? Oh, here. So it generates it in JavaScript, because that's what you program these robots with. So then I go to robot test. So these are script files that I prepared, which are basically just the scripts that can run on the robot. So say, let's grab this one. I don't think I will use this anymore. So I can just copy these movements into here. Get rid of the white space. Save it. And then I can plug this into here. I'll have to move this as well. I hope this is the mouse. Yes, it is. Great. Okay, so let me just save your file real quick. Save. And add a new file. So say robodk. So what I can do now is in commands, you have more advanced scripts, and you can actually implement a script. So in here, you can also program with JavaScript. But of course, we did the robodk did the programming for us. So we can load, take it from the SD file, and I think I put it in this one. Yeah, 12th of April. So you can just load your code into here, do a validation check, apply, and then if we run it, yeah, that's what we did in robodk. No, you can't. You can't. Well, you can. I think there's a simulation robot here. I'm not sure if this will work. Let me see. I've not tried this out actually. So if we run it from here, okay, so we can. So you see now, I don't know if you can see it. So it's on the screen, it performs it over there instead of the real robot. So you can simulate it. But now, if we go onto the real robot and we apply the exact same script, then it should perform the exact movements that we did in robodk. So it moves to one position, and it makes a stretch, then it goes to its home position again. Great. So now, of course, these kind of things are quite easy to do in robodk and are not that advanced. But I do have some examples of robodk. Let me see here, which is quite advanced. So this is an example of a universal robot, which actually has a CNC milling machine. And if we run this program, we can actually see that it picks up some products. The door opens, it places it inside. So this is, of course, a way more advanced way of offline programming. So you simulate your So you simulate your entire environment inside of the software, and then you can program your robot. So in here, you have the program, and you can just export the code and upload it to the robot. Sorry?
How much is the license for a robot?
I'm not sure how much a license is. I think you can also use it for free, but you're limited to like 50 movements inside of the program. So of course, for something like this, it's quite advanced, but you can also make more projects, of course, and collect those and upload those to the robot. So, but you also have. So I took RoboDK as an example because Hanwha works a lot with it. But at MIT we use ROS a lot, which is quite a similar program, and I think that that's for free. So you can also use that. But yeah, here you can make a quite specific programs. So you can even see right here that the products have actually been mailed. So yeah, and then for the last assignment or exercise is is that I built this. So I basically made a block which has the exact dimensions of this table right here. And I would like to ask you to write a program which moves the tool to each of these three corners. So it pinpoints exactly this corner first, then moves to this corner first or second, and then to that corner. So quite, you should be able to do it quite accurately.
So you need some targets then, I guess.
Yeah, correct. So
where do I put it?
what you can do, so I have the home target. If you zoom in a little bit, so you can zoom with the scroll wheel. With the right wheel, you can rotate around it, or with the right mouse button. Yes. So what's quite confusing here is that you have two arrows. So one is for the target and one is for the tool center point. So what you can also do is right click on the home, because that's already set, and then you can deselect visible. Yes. So now you can move the robot anywhere. So if you place a target, it will place it on the tool center point. So you can, for example, if you hold Alt, the Alt key, then you can drag the arrows, and then you can move the robot.
So and how do I get? Should we just position it like just from like viewing it, or should we actually put in like exact coordinates of the corners?
No, just by viewing it. Yeah. So for now, we're not doing it that precisely. But what you could, of course, do if you double press on the table, for example, if you double click, then you can really precisely put in coordinates. But for now, we're not going to do that. Okay. So you can indeed, if you have some kind of thing, you can make it up to a bit millimeter precisely.
So is this sufficient, or should we?
Well, yeah, if I would put it like down as well. So make it go really precisely to one of the corners, to each of the corners. So you can make it go down even further. Yeah.
Like this?
Yes, like that. And then when you press the target button, it will implement a target right there. You can give it a name or not, whatever. Target 2 is fine, fine, of course. So yeah, that's your first target. Nice.
What did I do now?
Yeah, I think you grab one of the rotational arrows. You can always just move it to home to like reset it. If you double press it, I think. Yeah.
Okay.
Yeah, it's quite annoying. The rotational arrows will mess it up. So you can, for example, now use this blue rotational arrow if you press Alt to like align it with the
Which, this one?
yeah, this one. Yeah, you can move the tool so you can like align it with
okay,
like
yes,
this
with the-
side. Yeah.
Okay, I see. Yeah, to reach this.
Yeah, definitely. I can imagine.
Something like this.
Yeah, looking good, looking good.
And so we set a new target.
Yeah, add a target indeed. So that's your third target.
So this corner again.
Yeah.
So
Yeah, that can be quite annoying. I would suggest just moving to home, double clicking home again. Yeah, then we'll move there and just take it from there. I
like this.
Yeah, looks good. So at your fourth target, great. So then we want to add a program.
Yep.
Yeah.
What's actually this?
Yeah, you can also add Python programs. So you can program some robots with Python as well.
Okay, so this is our
Yeah,
program.
so
or
this is your program. So these are just reference frame and tool settings.
this one is the
So-
home, or
Yeah, if you press on it, double click on it. Yeah, so I think because you are on target, I think you had target 4 selected, so it immediately made a 1 for target one. But you can right click it, and then target linked, change that into home. So then if you double click it, it moves to its home position, and then you can just yeah, with those 3 buttons on top, you can make jog or linear movements, or a circular movement, but not used very often.
then we always have to assign like the targets.
Yeah, you can also move to a target and then add the movement. But oh yeah, so because now because you didn't have anything selected, it added a new target.
Oh,
So you
okay.
can just delete that.
Delete it.
Yeah, delete. So and then link that to whichever target you'd like to go to first.
If we select this.
Yeah, target 3. So now if you press on move, then it should add target 3. Yes, correct.
Okay. then home again, or?
Well, no, you can if you'd like, but of course this will be repeated, so it will move to home again.
Okay.
So you can look at how it looks by right-clicking the program, and then press run. So yeah, it should move between those corners.
Okay.
Okay, so then we right-click the program again, and then say generate robot program.
Generate here, or?
Yeah, that one. Yes. And then we have to add it. It's quite inconvenient, but so these. So these are just settings. If you are connected to the robot, it will have to tell the robot like which reference frame to use and all that kind of stuff. But for now, we don't have to. So let's replace the white spaces. So grab this. So let's play. Oh wait, let's place it here again. Paste it into there. So I can also take out this cable so we can look at it on the teaching pendant instead. So now we have it right here. So same thing, script, stop this script, edit, load in the file. Robot test. This one we had selected, I think. Yes. So apply it. So now it should go to each corner. So the home position. Okay, nice, nice. Great job. So yeah, as you can see, this is of course quite an easy program. But if you have just rough imports of what your environment looks like, you can actually make quite complex programs. So what you can also do, for example, this is also a nice way to look at the difference between the linear and jog movements. So you've just implemented jog movements now, but let's say we change these. So move to the first target, then make that a linear move, and this a linear move. So then you can see, yes, that looks good. Save it. Oh wait, what's going on here? Okay, so I think it's already seeing a problem here. Because one thing that you have with the linear movements is that it uses, for this movement, as you can see, it uses all of its joints to make quite a complex move here.
Yes.
So it can keep the tool steady. So then it can run into singularities, they call it, which is an error. Yeah, if it performs if it needs to perform some kind of movement that it can make, just to keep the tool steady. So I think, I'm not sure if it will work here, but I guess we can just try. So generate the program. No. so. So if we do the same thing, we load the file in. Clip corners. So then you should be able to see that it's quite a big difference between the linear and the jog movements. So we'll first move to home. So that you can see it follows along the line really linearly and through the middle as well. So first it was making these big arcs. I think it's just barely making that last move. Because of course the speeds of each joint are limited, so I think it's nearing its limits. But it works, so great.
Yes.
Nice job. So yeah, that was basically all I had planned for my presentation for the course. So I want to thank you. And if you want to play around with it a bit, then go ahead. Or if you are at the Tech Hub at any time, then you can just walk up to our office, or just play with it yourself. So yeah, thank you. Of course. Great. It's quite odd that you were the only participant, but we made it work. So
The other courses, there were more people, or?
yeah, so I think for next week we have 2 people, and like I said last week, there were 20 people. So those were from denticulation. So we actually had to split it into 2 groups because 20 people would be too much to let people program and stuff. So I did one in the morning and then one in the afternoon with 10 each. And for today we had 3, but one cancelled, and Ruben Ruben paid attention last week. He was here as well, so I think he got most fit then as well. Yeah, definitely got the most programming time. So I will just stop the stream. Hey.